surrounding a permanent magnet, there exists a magnetic field which can be represented by the magnetic flux lines similar to electric flux lines. The magnetic flux lines differ from electric flux lines in that they don't have an origin or termination point. The magnetic flux lines radiate from the north pole to the south pole through the magnetic bar. Then we are having the magnetic field lines, as we have earlier discussed that the lines are traveling from north to south. If we use the compass as it is shown in the diagram, if we are using the compass, then we can easily draw the magnetic field lines or the flux lines of the magnet. So we can describe this magnetic field lines by using a tiny compass placed at the nearby points. The direction of the magnetic field B at any point is the same as the direction indicated by this compass, and the field B is strong where lines are dense and weak where lines are sparse. So the field lines between the magnets, if we see the lines between the unlike poles, because one is the north pole and other is the south pole, the lines, magnetic lines of force will travel from north to south, and they would be look like this. Due to the unlike poles, there is attraction, force of attraction is there. So the magnetic lines of force are leaving N and it is entering S, that is leaving the north and entering the south. But in the unlike poles, but in the like poles, as we see, north and north, they will repel each other. There will be no attraction, but it would be repulsion would be there. So in the magnetic fields, again the continuous magnetic flux lines will strive to occupy as small an area as possible. The strength of a magnetic field in a given region is directly related to the density of the flux lines in that region. If unlike poles of two permanent magnets are brought together, the magnets will attract and the flux distribution will be as shown below, as we can see in this diagram. Because two unlike poles of the permanent magnet, they are brought together, magnetic lines of force are starting from north and ending at south, then again starting at north and ending at this south. So we can see the magnetic lines of force traveling from north to south and then again from north to south. So again in the magnetic field, the space around the poles of the magnet where magnetic force is felt is known as the magnetic field. This field is represented by the magnetic lines of force. The force in the space around a magnet can be visualized by placing a card bound on a magnet. The pattern can be pictured by iron fillings sprinkled on the card, as the pattern is shown in the next slide. So, this is the pattern. As if we are having small iron pieces, then we can draw. So, this is the permanent magnet, and we are having the iron fillings over there. We can easily see the magnetic lines of force over there. This is the natural picture from where we can assume that this is the magnetic field. Then we are having the flux and flux density. In the SI units, the system international units, the magnetic flux is measured in Webers, and it is represented by a symbol phi. And the number of flux lines per unit area is known as the flux density, that is capital B. And in the SI units, the flux density is measured in Teslas. Tesla are the units to measure the flux density. So, its magnitude can be determined by the following equation: B is equal to phi upon A, where B is the flux density in Teslas, phi is the flux in Webers, and A is the area in square meters. So, Webers per meter square, that is known as Tesla. Then the magnetic flux, each little iron splinter acts as a compass needle, attracting other fillings at its end and repelling those lying parallel to it. These lines of fillings led to the assumption that the space around a magnet contains number of magnetic field lines. These lines are collectively called the magnetic flux. Then we are having the magnetic force. Every piece of a magnet has two poles, one is north and other is south pole. The north pole of one magnet repulses the north pole of other. Similarly, the south pole of the magnet repulses the south pole of the other, and south pole of one magnet attracts the north pole of the other. Hence, if one brings one magnet nearer to another, there will be either attraction force or repulsion force depending upon the nature of their poles facing each other, and this force is called the magnetic force, and this force is directly proportional to the product of the pole strengths of the magnets and inversely proportional to the square of the distance between them. So, as we can see in this formula, F, that is the magnetic force, it is directly proportional to m1 into m2, and it is divided by d square, where m1 is the pole strength of magnet 1 and M2 is the pole strength of magnet 2, and D is the distance between these two magnets. Then we are having the permeability. It is the important property of magnetism of the magnetic materials. If cores of different materials with the same physical dimensions can be used in the electromagnets, then the strength of the magnet will vary in accordance with the core used. The variation in strength is due to the number of flux lines passing through the core, and the magnetic material is a material in which flux lines can readily be created and is said to have high permeability. So, in other words, we can say the permeability is a measure of the ease with which the magnetic flux lines can be established in the material. So, the permeability, it is denoted by mu, the Greek letter mu, and the permeability of free space, it is denoted by mu naught, that is the permeability of vacuum. Mu naught is equal to 4 pi into 10 raised to power minus 7 Webers per ampere meter. These are the units of the permeability, Webers per ampere meter. And the materials that have permeability slightly less than that of the free space are said to be diamagnetic, and those with permeability slightly greater than that of free space are said to be paramagnetic. Then the magnetic materials such as iron, nickel, steel, and the alloys of these materials have permeability hundreds and even thousands of times that of the free space, and they are referred as the ferromagnetic materials. The ratio of the permeability of a material to that of free space is called the relative permeability. Mu r is equal to mu divided by mu naught. This is the permeability, relative permeability. Then the density of the field lines, there is electric field, and line density is proportional to the change in n and change in area. Then the magnetic flux lines phi, that is B is proportional to change in flux and change in area. And the magnetic field B is sometimes called the flux density in Webers per square meter. Then the magnetic flux density is there, B is equal to phi upon A. The magnetic flux lines are continuous and closed. Direction is that of the B vector at any point. The flux lines are not in direction of force, but they are perpendicular. When area A is perpendicular to flux. Then the calculating the flux density when the area is not perpendicular, as we can see that there is an angle alpha. The flux penetrating the area A when the normal vector n makes an angle of theta with the B field is phi is equal to B A cos theta. and this angle theta is the complement of the angle that the plane of the area makes with the B field. Cos phi is equal to sin alpha. Then the origin of the magnetic fields. Recall that the strength of an electric field E was defined as the electric force per unit charge. Since no isolated magnetic pole has ever been found, we can't define the magnetic field B in terms of the magnetic force per unit north pole. We will see instead that magnetic fields result from changes in motion, not from stationary charge or poles. This fact will be covered later. Then the magnetic force on a moving charge. Imagine a tube that projects charge positive q with velocity v into a perpendicular B field. Then the upward magnetic force F on this charge moving in the B field would be there. Then the velocity would also be in that direction. And this experiment shows that force is directly proportional to Q, V and B. So each of the following results in a greater magnetic force F, an increase in velocity V and an increase in charge Q and a larger magnetic field B. Then the direction of magnetic force, if we see the right hand rule with the flat right hand point thumb in direction of the velocity V, fingers in the direction of field B, the flat hand pushes in the direction of force F. This force is greatest when the velocity V is perpendicular to the B field. The deflection decreases to 0 for parallel motion. Then the magnetic polarity, determine the polarity of an electromagnet. This is the left hand rule. Then the force and angle of path would be there. The deflection force is greatest when path is perpendicular to field and it is least when it is parallel. So we can see that the force is directly proportional to V sin theta. Then the definition of B field, that is experimental observations, shows that F is directly proportional to QV sin theta, or F over QV sin theta is equal to constant. By choosing the appropriate units for the constant of proportionality, we can now define the B fields as the magnetic field intensity B is equal to F upon QV sin theta. And a magnetic field intensity of 1 Tesla exists in the region of space where a charge of 1 coulomb C moving at 1 meter per second perpendicular to the B field will experience a force of 1 Newton. Then the forces on the negative charges. Then the indicating direction of the B fields. A field directed into paper is denoted by a cross, like trail feathers of an arrow. And a field directed out of the paper, it is denoted by a dot, like the front tip of an arrow. Then the crossed E and B fields. So, note that Fe on electron is upward and opposite E field, but Fb on electron is down, that is the left hand rule, and it is on the zero deflection if Fb is equal to Fe. Then we are having the magnetization curve, the BH curve, that is referred to as the magnetization curve for the case where the material is initially unmagnetized. The BH curve differs for different materials, and the magnetic materials have in common much larger flux density for a given magnetic field intensity. So, this is the construction of the BH curve started from here, from the 0 point. We will graph a plot between B and H. This is the saturation point from where we will come again to 0, as is we can see in the next diagram. Then we come in the negative region in the second quadrant, then again we will go upwards. So, this is the final construction of the BH curve. Then we are having the different magnetic units, the magnetic flux density, that is Tesla, its symbol is B. Then the magnetic flux, that is unit is Weber and its symbol is small f. Permeability, it is Weber per ampere turn meters, it is denoted by small m. Reluctance, ampere turn per Weber, it is R. Then the magnetomotive force, or MMF, ampere turns are the units and symbol is Fm. Then the magnetizing force, that is ampere turns per meter, it is denoted by capital H. Then the determination of the BH curve. Basically, we are having two methods for the determination of the BH curve. First is the method of reversals. A ring shaped specimen with known dimensions are used for this purpose. A layer of the thin tape is put on the ring and the search coil is insulated with wax. Another layer of the tape is put over the search coil and the magnetizing winding is uniformly wound over this tape. After demagnetizing, the test is started by setting the magnetizing current to its lowest value. The value of flux density corresponding to this H is calculated by dividing the flux area by the area of specimen. Then the determination of BH curve by step method. This it is the circuit is shown in the next slide. This is the determination of BH curve in the step by step method. This is the BH curve. Then the determination of hysteresis loop, they are having again two methods. First is step by step and second is the method of reversals. This is the determination of hysteresis loop by method of reversals. This is the hysteresis loop. Then the wattmeter method for iron losses. This is the wattmeter method. Then the Lloyd-Fisher square. Then the Epstein square method is there. So, this is the flux density measurement and the magnetizing force measurement. So, this is all about the lecture. Thank you very much.